used in practice. So the basic idea is that we have that every project, every investment that we have, whether it's a real investment or financial investment, is characterized by a stream of cash flows. And we can compute the present value of these cash flows by first of all taking an expected cash flow and then discounting it by a risk-adjusted discount rate. So that was kind of the key logic here. So one question that was still open and that we're basically tackling starting next week is how do you come up with this risk adjustment in the discount rate? There's a theory around it, the capital asset pricing model, that we're going to dive into great detail here in this class. So the key principle is you estimate your cash flows, you forecast, and then you figure out what the discount rate is. And basically the risk of the cash flow has to match the risk adjustment of the discount rate. So that's basically every valuation problem runs down to that, to figuring out these two things. We'll study a second method today, which is not something totally inconsistent, but it's just sometimes a way to get to the result quicker. Or if you have some problems with the present value method. Some problems might be that you, for example, don't know what the discount rate is. That's just a missing information. And the other one would be if the discount rate is not kind of constant. There might be cases where the discount rate is changing over time, for example, when the risk of something is going to change. So the stock options that we're going to look at. But you could theoretically use the present value approach, but it would be very messy and very difficult. So we use this other approach that we studied today to make things easier. Right? But what's important is that they're not inconsistent. They're just based on different information, but should always lead you to the same result. So I hope that you have seen present values sometime before. If not, that was a very quick review last week. And there are basically two application examples of this, which I want to discuss with you this morning. So maybe let me first see, I know that there are students with different levels here in the class, so are there any questions remaining from what we've done last week? Okay, so that seems fine. Maybe these questions pop up if you start working then on the problem sets, and we can come back at any time. Right, so if it's short questions, I don't mind answering them via email, but if you have longer questions that might kind of require me to go back to some material or explain it differently, I'm always happy to carve out like 20 minutes or so in a lecture. Because if one person has a question, I bet that many others have the same question and wonder about the same thing, so it makes more sense to discuss these in class. Good. So the second example was your homework, but we skipped this slide here last week, so let's quickly work on this one here. So the idea is to compute the value of a cash flow, which at first glance seems to be very complicated to compute the value. Like if you go back to our initial formulas that we have here, the formula requires you to, for every cash flow that you have, create the present value and then sum those things up. So of course you could go and use this formula here. However, what makes this here difficult is that you actually have 25 years. So if you want to do this using this formula, you would have to kind of compute 25 of these discounting factors and then add them up. Of course, in Excel you can quickly do that, but there is another way to do this in short. So the stream of cash flow that we have here is a coupon bond. So for 25 years, you receive a coupon of 5% multiplied with the notional of 1,000. So the cash flow that you have every year is 50. And then at the maturity date, you get your notional back, so in 25 years. For simplicity, we just use the constant interest rate of 12% throughout this. So last week, we discussed a cash flow that was called a perpetuity. So that was a constant cash flow that you receive until kind of infinity, until eternity. The stream of coupon payments here has a different name because it's also a constant stream of cash flows, but there is a maturity date. It ends at some point. So this is called an annuity. Right? So perpetuity is forever, and annuity is something that stops. Right? So the idea is to use the formulas that we derived last week to compute a quicker formula for the annuity. So one example you see here in the valuation of long-term bonds. Another example where this is really important is when you take a bank loan. Because usually if you kind of borrow money to buy, say, a house or an apartment, you borrow for very long time periods, 15, 20 years or so. And the way you have to pay back to the bank is by a constant payment every month. Right? So that is an annuity. So you could use this formula to compute kind of the relationship between interest rate, your loan amount, and how much you have to pay per month back to the bank. Right? So there's a fixed relationship, and you can use this formula for this application. So that's probably the most commonly used application of this formula is for bank loans. Okay, so as I said, you can use the standard formula and do this kind of in Excel pretty quickly. Actually, there are implemented formulas in Excel for bond valuation, so you just kind of plug in the dates, you can put in the Descartes convention, and Excel does all the work for you, so you wouldn't actually have to do it manually. But let's try to apply the formulas that we studied last week to simplify this. And the formula which I want to apply is actually this formula here. So I want to actually use the perpetuity formula. And remember, the perpetuity formula has a growth rate of 0, so it's just the expected cash flow divided by the interest rate. I want to apply this formula to solve this valuation problem that we have at hand here. So maybe let me first kind of write down the stream of cash flows that we have to illustrate this a little bit. So the bond, this will be the bond cash flows. Then we have, say, 20, 24, 25.
Chắc mình có cho nhanh rồi. Ôi thiệt, có thì một quá. Lớp này có thấy nhiều bạn lạc ghê luôn.
So I deliberately put in a year here, 26, which is longer than the bond maturity because I want to write something to the right-hand side as well. So let's first write down the cash flow of the bond. Where's this here? So the bond will be in blue here. The first cash flow that we get from the bond is after 1 year, so that will be here. That's our coupon rate times the notional amount, so that's 50. I received another 50, and so on. In year 25, I again received 50. And then at the end, I get my final coupon payment plus the face value or notional. And then we have 0, then basically this thing ends. Okay, so one thing that we can easily compute the value of is the 1,000 actually here, so the notional amount. Maybe I should take the notional out here. The 1,000 is not the problem. The 1,000 is pretty easy to calculate. What I want to use a shortcut for is these stream of 25 times 50. I want to develop an easier formula together with you for this. And I've said, but maybe we could use the perpetuity because it seems related. So maybe just first write down the cash flows of the perpetuity and see how this ends up. So the perpetuity, and let's assume it's also 50, would give me 50 here, 50 here, and so on. It gives me 50, another 50. And now the problem is it doesn't stop, right? It continues. Let me get rid of the 1,000 here. We put it back in the calculations, but I think for the computation that I want to do, it's easier if I write it this way. So the thing that I want to write here is just the coupons. So we deal with the space value separately. That's easy to do. Okay, let's compare these two streams of cash flow. The first line ends at 25, the second line continues. So actually, the perpetuity formula is fine for the first 25 years. It gives us exactly the number that we want. However, there's even more included in the perpetuity. So let's write another line here. Let's compute the difference of the two. So the difference here is 0, 0, and so on. 0, 0. And here the difference is going to be 50. And it continues to be 50 in the future. Now, why did I write this down here? Because actually, if you look at this difference, this is a constant stream of cash flows of 50, but it doesn't start here in year 1, it starts in year 26, right? So actually what we can do is you can apply the perpetuity formula on this stream of cash flows. We'll go back quickly to the definition of the shortcut formula here. So the present value that you have here gives you the present value basically